Thank you very much, Marco, for your introduction. And yeah, let me start by thanking also the organizer for this very great opportunity to talk about this work, which is a joint work with Mete from ETH Zurich and Frank Riedel from Universität Bielefeld. The title is slightly different from the announced one, but the topic is the same. It's just that I realized that in the previous title we were declaring somehow what we were doing new, but also actually this framework includes also some less recent frameworks, and so actually a more generic title would be more appropriate, in this particular viability, arbitrage, and preferences. Let me go through it and tell you exactly what I mean by those names, and this goes back indeed to some less recent stuff, which comes from the 70s, late 70s. So we want to answer a very simple question. So suppose you are giving me what I call here a price system. So I have a set, So I have a set capital X, which represents the whole claims that I have in the market. And I only know something about a subset of them, which I call market claims. And for these market claims, say replicable claims, for example, I have a linear pricing rule, which is defined on M, and so I know how to price this stuff. Okay, this is something that I know, so please tell me something that I don't know, and indeed what I want to know is actually how to extend this pie to the whole space, because I want to price claims which are also not market. So this is a very fair question, and possibly we would like to answer this question in a way that this extendability somehow follow from some economic principle. So what is the economic principle that these authors has been investigating is this viability. Let me explain you what this is. Okay, we have this couple, M and pi, and we say that this is viable if I'm able to find a preference with respect to which I'm able to find an optimal claim M star. Optimal meaning that it satisfies a certain budget constraint. So say that your budget is 0, otherwise you simply translate, it's not a problem. This particular M star has cost price which is less or equal than 0. And with respect to this preference, is the best one that I can take among my market claims, among those which are feasible, budget feasible. Okay, so sorry, this is not a star, but this is also an M. Okay, so this preference relation is telling me, okay, you are able to find among your market claims one which is best and which also satisfies your feasible budget condition. And why this condition makes sense? Well, because this is somehow a necessary condition for an economic equilibrium, because say that you have not this condition, it means that you're not able to find, for example, if you don't do anything, like trading 0, so M equals to 0 is also possible trading, so I don't do anything. This cannot be optimal, otherwise the condition should be satisfied. So I'm not happy of what I have today, so I try to trade, but whatever configuration I find, this is also not optimal, otherwise it would satisfy this condition. So as a necessary condition for this is a necessary condition for equilibrium because of this fact, and it also in some sense sufficient in the sense that if all the agents in the market would use this preference relation, then they would all be happy because there would be, it's not difficult to show that there will be a preference where no trade is preferred to trade, and so in particular everyone will not trade and everyone would be happy. So it's mostly necessary, but in some sense it's also sufficient. Okay, so what is the theorem is that this principle, this economic principle, which makes sense and should be somehow accepted to a very general extent, is enough for showing that I have indeed my extension from the market claims to the whole set X. Of course, I have to say what this preference, I was not very precise on that because, of course, if I don't say anything, then I can choose the preference where everything is equal, so then of course, you have something, you are able to find your optimal, but this preference should somehow represent your agents in the market. So you're trying to describe a certain trading system, and in particular, the preference which realize your equilibrium should be somehow a possible agent, a conceivable agent in the market. So let's have a closer look to what are exactly these restrictions. And of course, since it is in the definition, everything depends crucially on this class of preference where I try to find my conceivable agents. So in the work of Harrison-Kreps, in particular, by quoting, they say that the choice of a probability measure has three roles. First of all, it determines the space of contingent and claim that I want to price. Okay, I try to price all the L2 claims. It also plays a role in the choice of the preferences of the agents by saying what is positive, because I need a criterion to say what is better than what. And in particular, if I fix a probability, I say that something is better than something else if the probability of being better is equal to 1, for example, or at least positive. So this preference relation that I'm considering need to be somehow coupled with another object, which is a cone, which is telling me, okay, this is relevant, this is positive, and in particular, if I add this element to any element x, then I obtain something strictly preferred. So in the particular case of Harrison-Kreps, they were using the almost sure ordering for this. And also there is for their case, there is a particular continuity assumption, which says that the level sets are closed. I will not enter to details from here, but the sense is that this allows to make this extension to the whole space. And why this is nice, why this choice is particularly nice, because it has some consequences. And in particular, if I call down psi the extension to the whole space, if I'm working in a viable market, we say that these two sentences are equivalent, then I have that everything which is relevant or positive, if you want, is priced positive. So this is nice. This is what I expect to have. But the nicest thing is that actually this is a linear functional and continuous with, and I'm working in a L2 spaces. So this in particular says that this psi belongs to the dual, and the dual is again L2. So that in particular I can represent this psi via Riedel representation theorem. And this is telling me that this extension is not just an abstract object, but is exactly an expectation. And in particular, if this is a density rho, this is an equivalent measure with respect to P. And moreover, if then, I haven't said anything about these claims, but if they come somehow from a security market, so that I can also include all the trades, for example, in discrete time, then this also gives me a martingale condition. So basically, this is telling us that read in another way, is that viability is equivalent to P somehow admitting an equivalent martingale measure. So in a certain sense, this is a sort of fundamental theorem of asset pricing, but seen from an economic principle point of view and not from a no arbitrage point of view, which turns out a posteriori that this is also equivalent. Of course, this is a framework which works very nicely, but it relies on this choice of probability measure. So what we were asking, and it's the motivation of the paper, is that what happens if I don't have this P, or at least if I don't want to represent a market where all the agents somehow behave with the probability measure in mind, because we also have seen with this, several experiments that people are also reasoning with multiple priors. So we would like to understand what's happening if I don't consider a single probability measure, but what I want to consider is a more general framework where to study this viability, which maybe in particular contains also the framework of one probability, and how this is connected to these two questions, which is no arbitrage on one hand, and on the other hand on this extendability. So here I'm a bit imprecise. I will tell you later what do I mean by extendability. Let me just mention that with respect to no arbitrage, I was saying this is somehow obtained a posteriori, because in the original paper there is some discussion, of course, with respect to no arbitrage condition or no free lunch condition, but they turn out not to be really equivalent to viability. So somehow in the beginning it was also considered by Harrison and Kreps inside the definition of viability that there is some sort of arbitrage consideration. So it's not so clean, the relation between the two objects, the two concepts. Okay, so this is what we have been doing in this work, and what I'm going to present here indeed is this general framework that I want to discuss, how this is related to arbitrage and viability, and also this extendability actually means that I want to have a characterization in terms of what it will turn out to be only sublinear expectations. Okay, so the setup. So actually we have a financial market which is made of 4 objects. Actually the relevant one will be basically 2. Because omega is simply the set of all possible outcomes. Okay, this I'm messing up a bit the terminology. So then H is the set of all contracts. So this is somehow what I want to price, or the market in which I want to live. And the important property of this space H is this order relationship, which makes this space an order space, and which is telling us what is small or negligible and what is relevant. So this is somehow the analogous of what was before. Before we had the probability, which was telling us what is negligible, so null sets, and what is positive, so or at least non-negative, something which is greater or equal than 0 pure more surely, and positive if it has probability to be bigger than 0, at least positive probability. So in this case, we consider this order relationship as given, and which represents somehow what is unanimously considered negligible or relevant or positive from all agents. So this may as well coincide with a relationship given induced by a probability measure, but in general could be simply a weak order. Okay? In particular, it's telling us Z is negligible if the two relations holds, and non-negative if is weakly ordered with respect to 0, and positive is strictly if the converse in order doesn't hold. Okay, so this is the first object which is really important, and it determines somehow what is null and what is positive. And the other element which characterizes this market is this set I, which is simply generically called a set of contracts which are available at 0 cost. Or so in general are somehow your trading opportunities. If you want, you can think that also the price is already inside that by taking the payoff. I take out the price. So I look at the single object, which is a convex cone, which also means in particular that maybe I'm not in a frictionless market, so I'm not allowed to buy and sell, but also could be that I have some trading restrictions. So for us, the important thing is only that this is a convex cone. So this will represent my trading opportunities, let's say, and this is the unanimous order, which is defining what is null and what is not. Okay, please stop me if something is not clear. And the other object that we have to care about is what is the class of preference relation we want to look at. Remember that before the probability was also playing a role in the class of conceivable agents that we want to consider. And there was somehow some assumption on continuity, which maybe they were needed for the proof, but somehow maybe more difficult to justify economically. Here we are only requiring that there is a monotonicity respected. So if something is y is unanimously preferred to x, then also my agent will prefer y to x. We have some convex preferences. This is also standard in the economics literature. So if I prefer x to f and y to f, I also prefer the convex combination to f. And the last thing that we also need a continuity assumption, but I find this a little bit weaker in the sense that we are having a sequence of real numbers. So suppose they are positive and they define somehow a contract where I receive something for sure. So now if I have that I prefer y to x even if I remove possibly infinitesimally small sure amount of money, then if it happens for any n, so where this Cn is going to 0, then it has to be that I prefer y to x. So it shouldn't happen that I prefer y to x minus epsilon, so a very small amount of money, and then I don't prefer y to x. So this is the continuity that we need for the proofs. And now having defined the framework, we are able to somehow connect these two notions, arbitrage and viability. So first I need to introduce what do we need, what do we mean by this. So first let's start with the arbitrage condition. This is written in a different way, but somehow what we are used to have. It's called a free lunch with vanishing risk. I'm introducing here an additional possibly modeling tool, which is maybe I don't consider relevant everything which is positive, but only a subset of it. Maybe it will be clear later why I want to have this restriction, but this is possible that I don't think that everything which is positive is really relevant. Maybe I have something positive but so small that I get so small gain that I actually don't care too much about. And I call this a class of relevant contracts. So think if you want this R to be exactly P plus, so everything which is strictly positive. And when do I have an arbitrage or a free lunch with vanishing risk? If there exists a relevant contract, so something which is nice, and I'm able to, via a sequence of something which is available in the market at zero cost, by adding simple a vanishing cost, I'm able to obtain a contract which is weakly preferred to this relevant R star. So if you think of it as being positive with positive probability and always non-negative, this means indeed the usual thing, so that up to a sequence of tradable contract, I'm able to obtain something which it gives me a gain, but with vanishing risk. Okay, so this is the condition that we are going to use. And okay, this is what I was saying before. It is just a little break between the formulas. So we need to define viability. So we say that the financial market is viable if somehow is able to support an equilibrium. So there should be a certain preference relation which allows me to choose among all the possible trading possibilities and choose the best out of it. So in particular, it would allow me to choose what was before, remember the set M, I would need to find an M star which was in M. In this case, my trading opportunities are I, and I should be able to find an L star which lives in I, and such that if you propose me any other possible contract, then I will still prefer this L star. So to be more precise, this is the definition. So we have a financial market where we have these relevant contracts, and we say that this is a viable market if I'm able to find a preference relation in the class of preference relation that I was showing you. And I'm also able to find a net trade vector which is optimal. Optimal means that if I start with any position X and you propose me this contract L star, then this will be preferred to any other L. So you see, for the particular case of X equal to 0, this is exactly the condition. So this is the optimal. Moreover, remember that we needed also a sort of monotonicity. So if you give me something more, I should think that my preference should reflect the fact that I have more. And this is the content of this condition, which is that if I have my contract L star, and you take me away from L star a relevant contract, so something which is positive, then I will be unhappy, and in particular strictly unhappy. Okay, with respect to the previous case, we are only asking that this should hold only when I have really my optimal element. So I really like my optimal element, I shouldn't be willing to give away anything from it. And we needed to weaken the condition of respect to, for example, the classical Kreps and Harrison-Kreps, because indeed there was no equivalence with respect to the no arbitrage condition, which actually appears to be here. So in this case, it's equivalent that the market is viable in the sense that I was just presenting, and then it admits no free lunch. So maybe how much time I talked? Okay, 10 minutes. So I just want to give a small sketch of the proof. I will not go through it, but just what are the key ingredients. We want to show somehow, so the fact that from a viable market it has to hold no free lunch, it's clear, because if I have a free lunch, that I will not be able to find an optimal bundle, an optimal position, because if I have a free lunch, I will always willing to buy more and more of that, or at least the sequence of that. So the important implication to show is that if I have no free lunch, then I have a viability. And if I want to show viability, I need to construct a certain preference relation so that I have an equilibrium. So what I wanted to show is what are the key ingredients for the construction of this preference relation, and the key ingredient is this, what is called the super-hedging functional. So the super-hedging functional is defined in the usual way. So I find the least possible fixed amount of money, so that if I add to L, this is the unanimous order, so I unanimously prefer C plus L to X. And it's not difficult to show, this is basically by definition, that no free lunch is equivalent to the fact that this super-hedging functional has to give me a positive price for any relevant contract. Relevant contract, think still of strictly positive contracts. But why this is nice? Because basically the preference relation which will give me the equilibrium, so which will give me the viability condition, is defined basically exactly through this super-hedging functional. And in particular, okay, I have to change a little bit the sign because I want a utility function, so something which is, remember that I want the convex preferences, so it's a little bit with sign change, but the idea is that I evaluate my different claims according to the super-hedging functional, and in particular, I rate them by, if I consider the possibility to sell them, to give them away, I rate them according to their super-hedging price. So if the super-hedging price is higher, then it means it's a good one, so I prefer to keep it with respect to one which has a lower super-hedging price. So once you have defined this relation, then I will not go exactly through the calculation, but you can show that this particular preference has all the properties, the weak continuity, satisfy the equilibrium condition, and in particular it has strictly monotonicity with respect to relevant sets. Okay, so that is the main ingredient. And regarding the last, the other aspect of which is actually, okay, I have now viability equivalent to no free lunch with vanishing risk, but also what can I say about possible pricing elements, so in particular extended to the whole space. And what we obtain here is something which is actually a sublinear expectation. So in particular, okay, these are standard properties which are stated in the language of risk measures. So we have a sublinear expectation if, okay, we have some monotonicity with respect to the weak order. This is the unanimous weak order, so with this we always want to have it. Cache invariance means that if I add something which is a constant contract, this adds to my nonlinear expectation, and I have only, instead of additivity, I have subadditivity. What are the properties of this particular, and why we call it sublinear martingale expectation? Because it has to have a sort of absolutely continuity, which means that everything which is null, so remember that this set is the class of null sets, or sorry, negligible sets, which in the particular case of a probability are the null set. They have to be evaluated 0 by this nonlinear expectation. So this is a sort of equivalent to the absolutely continuity condition. We call it full support. What this would be the other way around. So everything which is relevant should be priced in a positive way. So everything which is relevant has a nonlinear price which is bigger than 0. Relevant, again, think of it of something which is strictly positive. And also it has this super Martingale property if basically the expectation of any achievable contract or trading opportunities, it has to be less or equal than 0. If it was if I was a linear space, then you would also have exactly equal to 0. In general, you will have just less or equal than 0, but this is again what it would be the equivalent of the Martingale condition. So if we now call this script M, depending on theta and R, sublinear expectations with these properties, then the theorem is telling us that we have a viable market is equivalent to no free lunch with vanishing risk, we said it before, but also it is equivalent to the existence of this nonlinear expectation, which basically is telling us that if you want to extend your pricing functional in the sense of Harrison-Kreps to the whole system, to the whole market, then you will not be able to have it in a linear way. You can have it if you work in their setup, of course, but in general, if you want to deal with uncertainty, somehow you will only find something which is sublinear. And the reason is, if you think of when you have a total uncertainty, so every possible prior is possible, then the problem is equivalent to the fact that you cannot find a measure which has positive mass on every point of an uncountable space. Uncountable, uncountable. We can say actually something more about this particular nonlinear expectation, and this is actually given somehow as a Choquet capacity, as a supremum of linear functionals. But these linear functionals now, they don't live in the countably additive measure, but in general they live in BA, so the bounded additive measures. So this, if you want to work again in this generality, we only say we can only have that. But they have the nice property that they were before. So okay, they measure one, the whole space, they measure positively everything which is positive. They have this Martingale condition, and also if I have a relevant element, then I cannot find a single element which assigns a positive price to any of the relevant elements, but if I choose a relevant element, I will be able to find one of these collection of linear functionals which assign a positive measure to it, a positive price to it. Okay, so and this is derived basically by duality techniques, very trivially, because we work for the moment. We have some extension, but we can think of a bounded measurable function, and that's it. Okay. So very briefly through the examples, I mean, I just don't want to say much. I just want to say that in this framework, it includes also some possible previous frameworks. So when you have a fixed probability measure, the weak market efficient hypothesis says that all the assets, if you are now working in a security market, all the assets have the same returns, which means in particular that the historical probability measure is already a Martingale measure. This is included in this framework if I take unanimous order to be the comparison of directly the expectation, so not the usual pure Mosher order, but the comparison of the expectation. And so in particular, the null sets with this unanimous order is those which are mean 0, and this means that in a viable market, the Martingale elements that I find are exactly the original P. There is no other choice. So this is what indeed the weak market efficient hypothesis is saying. The strong one is saying that it doesn't happen on the original historical measure, but it happens in an equivalent measure. And this is done with with this unanimous order, which is the one given by the usual P or Mosher order. So this is included, and this is of course straightforwardly generalizable to the case of ambiguity, because instead of having a single probability measure here, and I have a bunch of probability measure, and I take the worst case of when I do the linear pricing, And so in particular, this is a one-to-one correspondence between what would be a strong market efficient hypothesis under ambiguity, where I have that the preference relation, the weak order, is represented by comparison with respect to this capacity. So this is just a possible framework which is included in our setup, and where what is negligible now, it's not pure Morsure set, but P quasi-Sure set. And then, of course, also other possible cases are included. So you can include some pointwise preferences, and then you can choose your relevant sets. So then this is exactly what was the role of this relevant set that I was saying in the beginning. It was also to cover other possible arbitrage definitions that have appeared in the literature. This appeared in paper by Beatrice and Walter and other co-authors. This is also what appeared in Frank's paper and also in paper with Marcos. So this possible framework is also included in here. Okay, sorry, let me conclude here. Basically, we have indeed provided a general framework where might contain also possible markets where ambiguity or Knightian uncertainty is taken into account. And in this framework, we studied arbitrage and viability. And as I said, this allows for both. And in particular, we didn't say much about the possible trading instruments. So this could be continuous or discrete time, or also could be not a linear space. And indeed, also the dual elements that we find are not particularly nice. They are in BA. So we didn't say much more about that. We said indeed that there is an equivalence between viable markets and markets with no free lunch. And the fact that in general we might end up, if you want to have a pricing function which assign a positive price to any relevant element or any positive element, you might end up in something which is nonlinear. So this is somehow the effect of including the Knightian uncertainty, is that you pass from a linear extension to a nonlinear extension. So this is somehow the price to pay if you want to consider that. Okay, that's it. And thank you for your attention.
No, I just, it's a long time that I haven't seen, having read the paper. Ah.
Thank you. Just push, right? Just long. Push.
So, yes, now I was saying it's a long time that I haven't, that I read the paper by Kreps and Harrison-Kreps, but in the proof of Kreps, the proof of no free lunch and viability, they do a functional analytic proof, if I remember. They don't pass at all through the super replication price. So the technique that you are using is completely different from the one they applied. It's based on...
Yes, indeed, because the idea is that the proof that they're providing is very nice indeed, and relies entirely on functional analytic techniques, as you were saying. The price to pay is that actually they need to consider agents which have a sort of continuity assumption on the preferences, and so in particular that these level sets are closed because they want to do a separation theorem. And so what we somehow didn't find it too nice is somehow, or at least more difficult to justify this continuity assumption with respect to a weaker continuity assumption. And so we needed to use something completely different. And of course, this works if you are, this techniques works if you're working in a nice space. And so, yes, this doesn't work in this case.
There are, yes.
In
Can you show the last slide again?
The very last one, this?
Yes. No, okay, the one before, yes, okay. No.
This
one, yes, okay.
Okay.
So, I mean, your pricing mechanisms are in BA in general, which is not very nice. So, under which extra conditions on the setup can you get something that is in CA?
Yes, yeah, that's a fair question. Actually, what is known more in this with the Knightian uncertainties the discrete time case is more developed, and indeed also the techniques that we have been developing with Marcus and also with Jan could be applied, and we have a last section on the paper on that. In general, I mean, starting from here, you don't gain too much in the sense that you cannot just say, I mean, this is simply the BA functionals that we find comes directly from the duality of the fact that we have a superedging functional, which is a convex functional, defined on bounded measurable functions, so the dual is BA, and we represent the dual, and we obtain the properties. So from that point of view, you don't start from here and obtain more by saying, okay, if I add more setting, then this particular techniques allows me to obtain more. For that, you might need to use exactly other techniques which are specific of the frame. This we wanted somehow just a general picture of what you can have, and then if you have your own framework, then you can use something else. Yeah.
So, any other question? Then we can thank both speakers.